circle, right? So like when I was at this point, right there, I know there's an x and a y coordinate. Yes, we can figure out what they are, but that red point would have depended on what time it was, right? When I actually drew it. So every single point on that circle could, if I wanted to, be visualized as being a function of time, which isn't even in the equation, is it? I mean, think about just the position of you on Earth at every point in time, right? Your position is a function of time, right? Where you are now is not where you were like 2 hours ago, right? So time could be visualized as being in the background. Understand? So is it possible for me to ask you what the derivative of x? Let's do. Yeah, we'll do dx dt. Could I ask you that question? And think about what that's saying. That's saying, can you tell me the instantaneous rate of change in the x coordinate with respect to time? It's not at, this is no longer looking at the slope of the tangent line. Because slope of tangent line was change in y over change in x, right? Change in y over change in x. This is no longer, that right there does not represent that. Slope of tangent line. What it represents is how fast your x-coordinate is changing with respect to time. So as this time moves at a certain instant, how fast was this x changing? And we could also ask ourselves how fast the y was changing with respect to time. We could ask both those questions. You with me? Kind of? Let's proceed. So if I want to take the derivative, I want to do it with respect to what variable here? T. And I want to do this on both sides of the equation, just like I did before. Do you notice that the variable that we are differentiating with respect to does not appear in the equation? Right? Yeah, it doesn't appear? T does not appear in there? In here? Well, when we were doing the derivatives prior to this, if we ever had like dx dx, it turned into 1, right? But dy dx didn't. Or the other way around, if it was dy dy, it turned into 1. If it was x dy, it did not. Well, these variables aren't the same, which means they're never going to turn into 1 when we use the chain rule. We'll never get a 1 to pop out. So let's just go through it. What would the derivative with respect to time of x squared plus the derivative of, with respect to time of y squared equals, what's the right side? This, fortunately, is always going to be 0, okay? I said that earlier, but now I'm really going to stress that. It does not matter what variable is changing. If that's always 16, its rate of change is 0, no matter what. So that's 0 still. What is the derivative of something squared? 2 times the something. Okay, chain rule. Times the derivative of the base, which is the derivative of what? X with respect to t. And I'm just going to write that down, dx dt. Whoa! That's what I wanted. But there's going to be a little bit of an issue. Because when you do this one, something else is going to pop out and we're going to go like, oh, crap. So we're going to have the 2y, right? But then we're going to get what? dy dt equals 0. This is what 2.7 in the book, this is what it's about right here. We're going to be differentiating almost everything in that section with respect to time. Because what we're going to have are physical situations that are changing with respect to time. You have a balloon that's getting blown up at a certain rate, and you want to know at a certain point in time, like how fast its surface area is growing, or how fast its volume is changing, or something like that. Okay, so almost everything in 2.7 will be with respect to a variable that does not even appear. All right, so what do I need in order to figure out dx dt? What is it that I'm going to need to know? Well, let's solve for it and let's analyze that a little bit. Okay, so if I try and isolate this, I'm just going to move these to the other side by subtracting them, right? Just move that whole thing to the other side by subtracting. So 2x times dx dt equals negative 2y times dy dt. And then I can divide both sides by 2x. 2x. So if I divide this side by 2x, divide this side by 2x, goes away, and you get dx dt equals, I can just cancel these, right? That's it. So I get negative y dy dt, all of that over x. So remember how I was drawing this circle? We started the clock and I started drawing the circle. And someone wants to know at a certain point how fast the x is changing with respect to time. Like how fast, x is left and right, yes? If I want to know how fast left or right that point is moving at a specific point in time, an instant, to know how fast it's moving just left or right with respect to the time means I would need to know a couple of things. I need to know the x-coordinate of where you are. I need to know the y-coordinate of where you are. And I also need to know what? How fast the y was changing when you were there. If you can tell me that, then I can tell you how fast the x was changing. So there's even more information that would be required for me to answer the question. Understand? This thing right here is something we would need to know. All right. Now the implications of this are I'm trying to think of a word, amazing. How many of you have ever seen this before? Raise your hand, yes? Where have you seen that before? I'm not going to quiz you. Where have you seen it? You saw it in algebra? Where else? Pre-cal? Chemistry. That's a famous formula in chemistry. It says that if you have a container, a closed container, like a Coke can, the pressure inside the container times the volume of the container must be equal to nRT. T is temperature. NR, anyone know what those are? No? Number of moles, and then Avogadro's constant. So, you could assume that in the problem you would know these would be constants. Avogadro's number is a constant. I think it's Avogadro's number. Look, I'm not a chemistry person. I think one of those is Avogadro's number. I'm a math person. Just tell me what the constants are, tell me what the variables are. That's all I need to know. So let's assume these are constants. Then P is a variable, right? P depends on what? The volume and the temperature. The volume depends on the pressure and the temperature. The temperature depends on the pressure and the volume. And this is actually, this formula, before I actually go and differentiate it, which is about what I'm about to do, this is actually a really cool formula. This is why air conditioners work. Okay? Your air conditioner, when you get in your car and you turn on your car and nice cool air, right? This is what happens. This is like a balance, right? Equations are like balances. That's a scale, okay? There's a scale, look at that. Here's PV on this side, here's T on this side, right? If you have a sealed container and you increase the pressure, I add more pressure, then the only way to keep this balanced is to add more to this side. So if you increase pressure, temperature must go up. Reverse that. If you decrease pressure, temperature goes down. Have you ever taken a Coke can or a Coke bottle and not shaken it up, but it's under a little bit of pressure and you open it? Have you ever noticed that the air that comes out is cold? Have you all ever noticed that? That rush of air out is cold, colder than the air that the ambient temperature around you. That's how an air conditioner works. What you do is you have this stuff called Freon, all right? And there's a thing called a compressor. And what happens is the Freon goes through this and it pressurizes the Freon. It puts it under high pressure. Right, I'm going to make a hose, okay? So the Freon's going through here. It's under high pressure, and then there's this little tiny little hole, this little orifice. And the Freon goes through this little hole, and on the other side of that hole is a tube. And on that side of the tube, there's low pressure. So there's high pressure. This is the critical place right here. There's high pressure right here. There's low pressure right here. So as it goes through, and it's like, I'm free. The pressure goes down. To maintain the balance, the temperature must go down. And that's what, it comes out, the Freon is really cold on this side. Then this goes through coils like this. And you have a fan, and you blow the fan over those coils, and that produces your cold air. Then it comes back through. By this time, it's not under pressure. Goes through the compressor, gets compressed again, high pressure, cold air. Back through, right? It's just a cycle. So it looks like it's free cold air, but where's the energy required to do this? You got to run the compressor, right? That's the critical piece. If you can't compress it, it's not going to cool anything down. They are expensive, right? And what's real bad is when that little orifice gets plugged up. Because when that orifice gets plugged up, then nothing flows and your compressor will burn out fast and lots of issues. Okay. Anyway, yeah, that's a little, I guess that's our mechanics lesson for the day. All right, so let's say I wanted to know here dV dt. What if I wanted to know the rate of change, the instantaneous rate of change in the volume with respect to time. So I've got some container, I've got some stuff happening, there's changes occurring inside of it. At a specific instant, I want to know the rate at which the volume is changing. Well, I start with the equation. I'm going to take the derivative with respect to time of the left side, and then I'm going to take derivative of with respect to time of the right side. Now watch how I write this. These are constants, right? So I'm just going to bring them along for the ride. Also notice little t is not capital T. Capital T is temperature, little t is time, okay? What about that left side? What's derivative of PV? Product rule. They're both variables. So it's going to be the derivative of the first one times the second plus the derivative of the second one times the first, right? There's your product rule on the left. Equals constants, NR, times the derivative of capital T with respect to little t would be 1? No, right? What is it? D capital T over D little t. It's whatever that is. I don't know what that is, okay? I'm telling you, I don't know what that is. But in order to figure out what dV dt is, I would need this. I would have to somehow get it. Now over here, what is this one? dP dt. None of these are going to turn into ones, right? Times V. This one is dV dt. R2 D2. And R D capital T over D little t. Yeah? And then what are we trying to look for here? dV dt. So there it is. It appeared, right? I'm not going to continue this, but what I would do is I would take this, right, this thing right here, I'd move it to the other side, and then I'd divide out this P on both sides, and I would have a formula for dV dt.
So you could just, in layman's terms, the dP dt times V, you could just put that in parentheses and take the whole time to it over.
Wait, put what in parentheses?
That one right there, the dP dt, that. Both of those in parentheses just for grouping purposes. and just move the whole chunk over to the other side?
It becomes minus over there.
Yeah.
Yes.
Okay.
Yeah, because they're attached by multiplication. So what I can do is I can just subtract that whole thing on this side. And notice there's addition between them. That's why I can do
The
that.
thing that was confusing me is there's not parentheses like usual, so I don't see the Greeks as much.
Okay, yeah. Well, the parentheses are not, you never are required to have parentheses unless you have addition or subtraction between two terms. And you want to bring them together.
Right.
Yeah. All right. So this opens up, I mean, the possibilities here are endless, right? I mean, you give me any equation in physics, in chemistry, and finance, does not matter. If you want to know about instantaneous rates of change, we have a way of figuring it out. All right? It's common sense. Boy, y'all are gonna not let me live that one down. So look, I've got a few more minutes. Y'all can pack up. I'm going to share a story with you all. I always share this story with my Cal 1 class.